The art of algorithm design, crafting efficient solutions in modern programming in an era where computational power is abundant yet efficiency remains paramount. Mastering the art of algorithm design has become essential for programmers aiming to solve complex problems effectively. This guide explores the principles that underpin successful algorithm creation. Whether you're optimizing data structures, tackling machine learning challenges, or building scalable web applications, understanding how to approach algorithmic problem solving can transform your coding experience from good to exceptional. Fundamental principles of effective algorithm design. At its core, algorithm design revolves around identifying patterns and formulating step-by-step procedures to address specific computational tasks. A well-designed algorithm balances correctness with performance considerations across various scenarios. Understanding time complexity through Big O notation provides critical insight into how algorithms scale with increasing input sizes. This knowledge helps developers make informed decisions during implementation phases. Correctness: an algorithm must consistently produce accurate results regardless of input variations or edge cases. Efficiency: optimal resource utilization ensures solutions remain viable even as datasets grow exponentially over time. Readability: clear code structure facilitates maintenance and collaboration among development teams working on shared projects. Problem analysis techniques for algorithm development. Before diving into solution architecture, thorough analysis of the problem domain is crucial. Identifying constraints and requirements establishes boundaries within which potential solutions must operate. Breaking down complex problems into smaller subproblems often reveals opportunities for optimization. This decomposition strategy enables targeted improvements without unnecessary rework. Evaluating constraints and requirements. Real-world application scenarios frequently impose limitations such as memory capacity restrictions or processing speed thresholds. Recognizing these factors early prevents costly redesign efforts later in development cycles. For example, mobile app developers must consider battery life implications when designing location-based services algorithms, balancing accuracy against energy consumption trade-offs. Common algorithm paradigms and their applications. Different types of algorithms excel at solving distinct classes of problems based on their underlying mechanisms. Selecting the appropriate paradigm significantly impacts both development timelines and final product quality. Divide and conquer strategies break problems into manageable parts, while dynamic programming approaches leverage overlapping subproblem solutions to achieve optimal outcomes. Greedy algorithms make locally optimal choices at each decision point, commonly used in scheduling and graph traversal contexts. Backtracking: systematically explore possible solutions by incrementally building candidates and abandoning paths leading to dead ends. Randomized algorithms introduce probabilistic elements to enhance performance characteristics in certain situations. Time complexity analysis and optimization strategies. Assessing an algorithm's runtime behavior using asymptotic notations allows engineers to predict scalability issues before deployment. This analytical framework identifies bottlenecks requiring attention. While Big O provides theoretical bounds, practical implementations may require additional profiling tools to identify real-world performance characteristics accurately. One constant time operations maintain consistent execution times irrespective of input size changes. N-log and efficient sorting algorithms typically exhibit this complexity class due to their logarithmic growth pattern. N superscript 2 quadratic time complexities indicate potential inefficiencies needing optimization through alternative approaches. Data structure selection for optimal performance. The choice between arrays, linked lists, trees, graphs, or hash tables directly influences algorithm effectiveness. Matching data structures to specific use cases enhances overall system performance. BSTs offer efficient search capabilities but introduce overhead compared to simpler array-based implementations for basic lookup operations. Trees provide hierarchical organization suitable for XML parsing or file systems navigation tasks. Graphs model relationships between entities ideal for social network connections or route-finding applications. Hash tables enable constant time lookups, making them indispensable for caching mechanisms and dictionary implementations. Design patterns in algorithm implementation. Recurring architectural motifs simplify complex problem-solving processes by offering proven frameworks for organizing code logic. These patterns emerge naturally from common algorithmic challenges faced by developers worldwide. Memoization techniques reduce redundant computations by storing previously calculated values, improving recursive function performances dramatically in many cases. Caching temporarily store intermediate results to avoid recomputation when identical inputs are encountered repeatedly. Lazy evaluation defer computation until absolutely necessary to optimize resource allocation dynamically. Pipelining overlap stages of processing to maximize throughput in parallel computing environments. Testing and debugging techniques for algorithm validation. Rigorous testing protocols ensure algorithms behave correctly under diverse conditions, including normal operation, boundary values, and unexpected failures. Automated test suites help catch regressions quickly. Unit tests verify individual components, while integration tests confirm interactions between different modules work seamlessly together. Stress testing subject algorithms to extreme load conditions to expose hidden vulnerabilities or scalability limits. Edge case testing validate functionality against minimal/maximal input configurations, ensuring robustness across all scenarios. Performance profiling measure actual runtimes against theoretical predictions to refine implementations iteratively. Continuous learning through practice. Problem-solving algorithm puzzles regularly sharpens problem-solving skills and deepens conceptual understanding. Online platforms provide curated collections of exercises ranging from beginner-friendly tasks to advanced challenges. Participating in competitive programming contests exposes practitioners to novel problem formulations requiring creative adaptations of standard techniques. LeetCode offers thousands of practice questions categorized by difficulty level and subject matter areas. HackerRank features interactive coding challenges with instant feedback mechanisms, helping learners track progress systematically. Kaggle competitions combine algorithmic expertise with data science know-how, addressing real-world business problems. Conclusion: mastering algorithm design requires dedication to continuous improvement through study, experimentation, and peer collaboration. By applying fundamental principles creatively, developers can craft elegant solutions that stand up to modern software demands. Embrace the challenge of refining your algorithmic thinking skills today. The rewards extend far beyond technical proficiency alone, shaping better problem solvers capable of tackling tomorrow's most pressing computational challenges.